Welcome to Increasing Data Center Efficiency through High-Density Power Distribution. For best viewing results, we recommend that you maximize your browser window now. The screen controls allow you to navigate through the e-learning experience. Using your browser controls may disrupt the normal play of the course. Click the Notes tab to read a transcript of the narration. At the completion of this course, you will be able to explain standard North American power distribution voltages for large data centers, explain power distribution voltages utilized in most parts of the world outside of North America, interpret performance data comparing rest of world voltages to North American voltages, share interesting observations that clarify existing power distribution practices and highlight potential benefits of an alternative method, and make general comparisons of power distribution alternatives. Market forces dictate changes to existing processes and existing systems. In the realm of data center management, the pressure is on to streamline operations through enhanced efficiency and to cut capital costs. An analysis of traditional data centers in North America reveals an existing entitlement in the area of power distribution. Upon inspection, the existing 120-208 volt distribution system is found to be somewhat lacking from a cost and efficiency perspective.
We'll discuss an alternative approach to power distribution, which is new to North America, but a standard in the rest of the world. This 230, 400-volt distribution scheme saves floor space, simplifies power cabling, saves capital cost, reduces weight, and increases electrical efficiency. This course describes this distribution architecture and quantifies the benefits. Please note that the methods described in this course only apply in North America and are for challenges that are unique to North America.
The standard power distribution system for large data centers in North America is a 277 480-volt three-phase power system supplying distributed power distribution units, which convert the voltage to the 208-volt and 120-volt single-phase branch circuits utilized by IT equipment. This arrangement is represented by the one-line diagram that we see here. High-density server installations, where racks can draw from 10 kilowatts to 40 kilowatts per rack, place significant strains on this standard power distribution system. This increased rack power density is causing multiple branch circuits per rack with corresponding breakers and cabling, PDUs to become up to 30% of the floor space, PDUs to become up to 30% of the floor weight loading, and more PDUs installed per IT rack, driving up capital costs. These challenges are unique to North America. In Europe and the rest of the world, the power distribution system is simpler and more efficient. This course will show that it is practical to take the power distribution system used in the rest of the world and apply it to North American data centers to reduce cost, reduce weight, save floor space, and increase electrical efficiency. In the past, it was not practical to consider alternative higher voltage power distribution systems because a significant fraction of IT equipment operated from 120 volts. However, in the modern high-density data center, virtually all rack-based equipment operates on 208 volts or 230 volts outside of North America. Even devices that can run on 120 volts are also capable of operating at a higher voltage. Virtually all IT equipment manufactured today is designed for worldwide compatibility. This means it can operate on the North American 120 208 volt system, the Japanese 100 200 volt system, and the 230 volt distribution systems used in the rest of the world. Let's begin by discussing an alternative power distribution method.
The alternative power distribution system proposed and described in this course is an adaptation of the power distribution system used in the rest of the world. This arrangement is represented by the one-line diagram shown here.
The differences between this diagram and the diagram previously shown are subtle and include three-phase branch circuit power distribution that is 230 volts instead of 208 volts, elimination of the PDU transformers, a transformer that is used to change 277 480 volts to 230 400 volts at the output of the UPS. Let's take a look at each of these differences now. First, let's look at three-phase branch power distribution, comparing 230-volt line to neutral to 208-volt line to line. The typical North American three-phase branch power distribution is at 120, 208 volts, while the rest of the world uses 230, 400 volts. This is shown here. While the proposed power distribution method sounds like a minor change, it actually creates a very large impact on the power distribution system. Servers draw their power from the 208-volt high voltage connection in North America, while they draw their power from the 230-volt low voltage connection in the rest of the world. It is important to recognize that when comparing the line-to-neutral voltages of both distribution methods, the comparison should be between 120 volts and 230 volts, and not between 208 volts and 230 volts. This line-to-line and line-to-neutral difference becomes readily apparent when the power capacity for a three-phase branch circuit is calculated. For example, assume 20 amp circuits are provided to the load in either case. The power capacity for the 120-volt line-to-neutral distribution method is calculated as 20 amps times 120 volts times 3 equals 7.2 kilowatts, while the capacity for the 230-volt line-to-neutral distribution method is calculated as 20 amps times 230 volts times 3 equals 13.8 kilowatts. Given the same circuit current rating, the 230-volt distribution provides 92% more power than the 120-volt distribution. This increases the power density capability per rack without adding extra circuit breakers, as would be the case with the 120-208-volt distribution. These additional breakers present additional points of failure, resulting in decreased data center reliability. Consider now the same comparison, except this time assuming a fixed branch circuit power capacity. For example, assume 10 kilowatts is available to the load in either case. The power capacity for the 120-volt line-to-neutral distribution is calculated as 27.7 amps times 120 volts times 3 equals 10 kilowatts, while the capacity for the 230-volt line-to-neutral distribution is calculated as 14.5 amps times 230 volts times 3 equals 10 kilowatts. Given the same power, the 230-volt, 400-volt distribution method provides the same power capacity with nearly half the current required by the 120-volt, 208-volt distribution method. This significant difference in current requires the branch circuit wires in the North American system to be 300% larger in terms of their size and weight. Next, we'll discuss the benefits of eliminating the PDU transformer. Even more important than the cost, size, and weight savings in wiring is the savings in transformers. The PDU transformers can be eliminated if the 230-volt, 400-volt distribution system is deployed. The PDU transformers are required in North America to change the voltage from the UPS output of 277, 480 down to 120, 208 utilization voltage. In the rest of the world, the UPS output of 230, 400 volts can be directly utilized by the IT loads without the need for an additional transformer. In a North American data center with 30 kilowatt racks, approximately 20% of space that would be available for racks is consumed by PDUs. In addition, the PDUs would make up more than 25% of the weight on the raised floor. It's important to note that these impacts were much lower in data centers of the past, which operated at approximately 2 kilowatts per rack. Therefore, the benefit of using this new power distribution approach increases dramatically as the rack power density increases. And finally, let's look at the third difference between the two distribution systems, a transformer that is used to change 277 480 volts to 230 400 volts at the output of the UPS. An additional transformer is used to change the UPS output voltage from 277 480 volt to 230 400 volt in the new proposed method. While it appears that this transformer replaces the PDU transformers, in fact, it is 90% smaller and less expensive than the PDU transformers for the following reasons. It is wired as an auto transformer. An auto transformer has only one winding, the primary winding, as opposed to two in an isolation transformer, which has both a primary and secondary winding. Therefore, the auto transformer is less than 20% of the size and weight of a standard transformer of the rated UPS capacity. It is sized to the UPS capacity, in contrast to the PDU transformers, which as a group are typically sized at 1.5 to 3 times the UPS capacity. In addition, this transformer can be located outside of the data center server space, such as in a back room, which further conserves valuable data center space. The auto transformer described in this new power distribution approach for North America can be eliminated in some cases, resulting in further savings. For new installations, the facility could be directly wired for 400-volt input from the utility company, and a 400-volt UPS can be used. If this is done, then the auto transformer is not needed. The disadvantage of this approach is that various related AC-powered devices, such as pumps, generators, and switchgear, are not readily available in North America at a 400-volt rating. Therefore, at this time, the preferred approach is to use the auto transformer as described in this course. Let's continue now by exploring a performance comparison. A comparison of conventional power distribution design with an alternative design was performed based on an actual customer's data center. Their data center is 2,175 square feet and consists of 2 redundant modular 600-watt UPSs. A total of 104 racks range in density from 1.6 to 6.5 kilowatts each. The results of this comparison are shown here. It's important to note the large savings in total cost of ownership and the large savings in space of the alternative approach of 56% and 32% respectively. The 10-year TCO savings by distributing at 230 volts is $166,335 or 56% savings. Of the TCO savings, approximately 49% is due to material cost savings and 51% is due to energy cost savings. There are some special cases where the alternative power distribution system is perceived to have limitations. The special case topics we'll address include occasional 120-volt loads, isolation and grounding, existing installations, connectors, circuit breakers, and three-phase IT loads. Let's discuss these cases and how the alternative distribution system addresses them. Data centers in North America encounter occasional 120-volt loads, even in high-density areas. These are dealt with as follows. Many 120-volt loads are actually 120 230-volt rated. These ratings are always on the devices. The vast majority of these devices have a detachable power cord. The solution is simply to change the power cord to a universal IEC C-13 or C-19 power cord. In some cases, it may be necessary to change a switch setting on the device. In cases where it is not possible to avoid using a 120 volt for isolated devices, a local rack mount transformer can be used to step down 230 volts to 120 volts. These are readily available in the market. The conventional North American power distribution system provides isolation of the neutral wire at each power distribution unit. This characteristic has historically been considered desirable and is given various names, including galvanic isolation, separately derived source, and regenerated neutral. Many of the claims regarding the benefit of this arrangement are not based on science. In fact, there is no data to suggest that data centers in North America are more reliable than data centers outside of North America, most of which operate according to the principles outlined in this course. The alternative system can be used alongside of existing standard power distribution and is particularly well suited for data center expansions focused on high-density server applications. The appropriate connectors for use with 230 volt circuits are IEC C13 and C19 types. This is the power cord connector provided by most OEM server manufacturers with rack mount servers and storage devices. Therefore, most high-density servers are already provided with the appropriate connector for use with a 230 volt system. Occasionally, a device may be provided with a power cord that uses a North American NEMA-style twist-lock connector. These are dealt with as follows. If the power cord is the detachable type with an IEC C13 or C19 connector on the chassis, then the cord should be replaced with a cord with IEC connectors at both ends. These are available from virtually all IT OEMs. Note that when substituting power cords, it may be advisable to purchase a cord of shorter than standard length in order to simplify power cabling in the rack. In the case where the cord is permanently attached to the IT device, if the plug is 20 amps or less, an adapter cable can be used. The branch circuit breakers used in the system described in this course operate at higher voltage than normal branch circuits in North American data centers. Most circuit breakers that are currently used in North American data centers are not rated for this voltage and cannot be used. Conversely, most European circuit breaker panels are not certified by UL for use in North America. Recently, manufacturers have introduced compact worldwide circuit breakers and circuit breaker panel boards that are rated and certified for high voltage use in North America. Many companies in the industry offer complete data center PDUs, remote power panels, and rack power panels that are appropriately rated and certified for high voltage distribution in North America. Very few IT loads are equipped with three-phase connectors. These include some compact blade servers, large EMC storage units, and mainframe-style servers. The key point to understand here is that none of these devices actually require three-phase power. In fact, all such devices actually use multiple power supplies drawing single-phase power. Furthermore, all of these devices have versions that are sold outside North America and therefore are compatible with the alternative power distribution system. These devices are addressed as follows. For large deployments of devices with three-phase power connectors, specify to the supplier that the power input is to be wired for European voltage. This is often a simple internal jumper setting. Determine if the device is field rewirable for European voltage operation. Many large devices are. If it's impractical to change the device or convert it, then consider using standard distribution to this device or install a dedicated PDU to convert the voltage for this device. The information in this course is provided to assist with implementation of the alternative power distribution system. Note that in the vast majority of cases, no modifications of any kind are needed to the IT equipment, the power cords, or the rack power distribution devices. Devices which are known to work seamlessly in the alternative power system include IBM Blade servers, 1U servers, virtually all enterprise rack mount servers, and virtually all rack mount storage area networks and network attached storage devices. What about DC power distribution as an alternative to AC power distribution? Let's explore that now. From time to time, DC power distribution, either at low voltage or high voltage, has been proposed as an alternative to AC power distribution. The hypothetical benefits of a DC system are claimed to include substantial increases in electrical efficiency. The system proposed in this course achieves many of the same benefits with much lower cost and complexity. Therefore, the high-voltage AC distribution system is a preferred strategy to improve data center efficiency. There are significant advantages to using a higher voltage power distribution system in high-density data centers in North America. Use of the international 230 400-volt distribution system instead of the standard 120-208 system can save 56% in the lifetime cost of the distribution system and save floor space and weight loading. The benefits are most apparent for high-density installations. Furthermore, the alternative design can operate alongside conventional power distribution designs in existing data centers. To summarize, let's review some of the information that we've covered throughout this course. North America faces power distribution challenges, while the rest of the world utilizes a power distribution system that is simpler and more efficient. An alternative approach to power distribution for high-density server installations will save floor space, simplify power cabling, save capital cost, reduce weight, and increase electrical efficiency. There is a significant savings of 56% in total cost of ownership, as well as a large savings at 32% in space when an alternative power distribution approach is utilized. The alternative power distribution design can operate alongside conventional power distribution designs in existing data centers. Thank you for participating in this course.